So we're going to start out really laying out the presentation objectives. What do we want you guys to get out of this? And I'm going to cover the first part of that, which is understanding the changing fire environment. Derek had mentioned it's not the same playing ground as it was when your fathers, grandfathers, great-grandfathers, depending on how many generations you have in the fire department, how it was different for them, how it's different for you today. Let's try and look at some of those things. Because ultimately, it's not, you're fighting a moving target. And we're going to talk about all the components that go into the complexity of that. Understand improve your understanding of fire dynamics. Weird word, fire behavior, fire dynamics. Really, fire dynamics is taking in everything that includes fire behavior, the structures that it's in, the materials it involves, all the physics behind what's going on. We're going to give you guys a better handle on that. Importance of size up and choosing tactics that fit the conditions. If you don't know what's going on, how do you know how to address the problem? And based on how the problem's changing, what are we seeing in the research as some tactical considerations to make you better today? Reevaluate your ventilation practices. In most cases, ventilation commonly gets overlooked because it's thought of this is just the thing that makes things better. Well, when you have an environment starved for oxygen and you provide that oxygen, the difference between a good result of ventilation and a poor result of ventilation could be the difference between 10 seconds, 20 seconds, 30 seconds, a couple minutes. Do you understand that timeline? And how do we coordinate that timeline so you're most effective? Understand the collapse hazard. We've done a ton of research on basement fires, and we're going to get into that pretty in depth. Re-examine your suppression practices. Where you start your attack from is very important. And we're going to talk about the differences between what you see when you show up and what the potential output would be of the tactical choices you make as far as where the hose line goes. Provide you more information to teach your members. Dan and I and now Derek have websites where we're putting all our information up. The purpose here is for not us to travel around teaching this stuff. It's for you to take it back to your department and to implement it. We'll make sure that you have access to all this information. And make you think more and ask why. If we're really going to improve as a fire service, we need to continually ask why we're doing things. And unless we understand why we're doing them, we can't have the smart firefighters and fire officers on the fire ground making the quick changing decisions that need to be made based on what you see. If we're a bunch of robots that all we know is how, and all we know is our SOP, and we don't know how and when and why to deviate from that or when to follow it or how what our size up tells us dictates what we do, then we're in trouble. And I think we can get to that why, and we can be smarter firefighters. We want you to remember these things. There's a big difference between theory and tactics. We understand that. It's very complex on the fire ground. But we're going to try and bound that problem and give you information that you can apply, or more importantly, know what your plan A is, know when to go to a plan B, and things along those lines. Engineers don't have all the answers. I know that's hard to believe. We can't run every possible scenario that you're going to respond to. It's impossible. There's not enough money, there's not enough resources, there's not enough of Dan to be able to do that. However, as you'll see as we go through this, the reason we're picking the scenarios that we do working with the fire service is that we can begin to bound the problem. And if we know what happens on this end and on this end, we've got a pretty good idea what goes on in the middle. And if we start seeing the same trends over and over again, a lot of what we're going to present isn't from one test in a lab. We're up into the over 100, probably approaching 200 full-scale experiments, whether it's single-family houses, townhouses, full-scale stuff in our lab, acquired structures, stuff in cities, stuff in suburbs, big buildings, small buildings, high-rises, and everything else. The physics doesn't change, and we're beginning to put all those pieces together, and that's what we're sharing with you. There aren't enough fires to make you an expert. The one thing that we can do in research that you cannot do in the field is, all right, I'm going to show up. I've got this very simple 1,200 square foot ranch house on fire. I got fire in the AB corner. I'm showing up. I got smoke showing. Lines going through the front door. Fire goes out. Was that the best way to do it? What if you would have vented opposite the hose line, or what if you would have cut a hole above where that fire was as you were moving in? Would that have been better? You'll never know, because you're not going to that same 1,200 square foot ranch house with the same fire in the same spot to pick a second choice. You don't get a second choice. In research, we do. We can get 20 choices on the same fire, and we can say, well, I didn't want to vent the AB corner. Let's see what happens when I vent the CD corner. Or what happens if I VEIS the back bedroom while the hose line's going through the front door? What if I make a 4x8 hole instead of a 4x4 hole on this fire? You don't get to do those things. You go to very different fires. You could go to 10, 1,200 square foot ranch house fires, and if the fire's in a different spot in the house every time, you may get a different response from your tactics. How do you put those pieces together? Well, we can do it through education. We can do it through fire behavior knowledge. And now's a really good time. I think for a long time, all the fire training books had the how to do things. Here's how you force a door. Here's how you break a window. Here's what ventilation is. Here's what suppression is. Without a lot of details, because the information didn't exist. Well, fire dynamics research picked up on the fundamental side, so we understand how fire grows and spreads. Money became available through different sources to do research with the fire service. We took advantage of that, so we took the principles and we started to apply them at a full scale. And then we got a whole bunch of engagement from the fire service saying, we want to know these answers. So we started putting these three groups of people together, and really what you're seeing today is the results of that. So let's talk about today's fire environment. What's changed? The important piece here is it's not any one component. Houses are getting bigger. Spaces are becoming more open. Fuel loads are evolving. Void spaces are changing. Building materials are changing constantly. And new technologies are being integrated into your work environment every day. Any one of these could present a serious problem for you. The difference is they're all coming together at the same time, and they're all changing extremely rapidly. Can we understand how that impacts our operations? Well, ultimately, you put them together, and you start getting fires that are growing faster than they ever have, civilians with less time to get out than they've ever had, structures that are falling down around you quicker than ever, and hazards that you may have never even seen before that you need to be experts at because someone's calling you to deal with their problem. Let's look at all of them real quickly. Home size increased from about 1,600 square feet to 2,600 square feet over the last 40 years. Is your staffing of your department increased because the hazard's increasing? More than a quarter of the houses built in 2008 were greater than 3,000 square feet. Have you changed the complement of firefighters that you have responding to those incidents? In many cases, probably not. Open spaces. This one kind of goes hand in hand with the changing building materials. So what we used to have was dimensional lumber. You could only span so far with dimensional lumber. So now let's say the most you can have is a 16 or 18 foot span to make a room a certain size. Then we went ahead and we developed I-joists and trusses and things like that can span a whole lot longer. So now with the dimensional lumber, we need a whole bunch of bearing walls. Now you don't need those bearing walls. Now families enjoy open spaces. So now you have rooms inside houses that used to be confined and compartmented, which could compartment the fire and work in your advantage. And now all that compartmentation is being ripped out. Any one of you has probably removed a wall in your house or bought a house with an open floor plan because that's a popular thing these days. That's something that we want. It's going to change how that fire responds. Great rooms. You now have 15 to 20 foot ceilings in houses. You think the same fire development is going to happen in an 8-foot ceiling as it is in a 16-foot ceiling? Different things are happening before you get there. If you've got line of sight, that fire's got line of sight. If you now have a first floor of a house that's completely one compartment, your fire flow may be different than if you pull up and you've got a 12 by 12 front living room on fire or a small bedroom on fire. It's going to change how your water interacts with that problem. Evolving fuel loads. This is a big one. We're moving from a natural to a synthetic dominated environment. The potential energy in the fuel is very different. There's more there to be released, and this is where you're going to start hearing the term heat release rate. Because the speed at which that energy is able to be created is your problem. Temperature is just the end result. Temperature is because the energy got released. So if the temperature is 1,000 degrees, it's going to be 1,000 degrees whether you're burning cotton or whether you're burning polyurethane foam. The question is, how quickly does it get to that point of flashover? How quickly does it get to the point where you're running out of oxygen to burn that it's going to get from your operations? So we've got a neat lab in Northbrook, Illinois at UL, 120 feet by 120 feet with essentially a large aircraft carrier deck as a ceiling that we can move all the way down to the 5-foot level or all the way up to 60 feet, and we can simulate different warehouse configurations. Well, when we're not running warehouse configurations, I've got a little playground. I can pretty much build anything. So we start out small. Here's a couple rooms side by side. Modern room, legacy room. Modern room is stuff that I went up the street and bought. Legacy room is I went on Craigslist and I tricked old ladies into selling me their old stuff that you can't find in the store anymore. You put those two things together, you get a very different fire scenario. So you can see on the left-hand side, there's your modern department store sponsored room. On the right-hand side, we did take the plastic off of Grandma's sofa, so you've got cotton-covered cotton batting in the furniture. It also has furniture that was actually made of solid wood. Good luck finding that today without paying a huge premium for it. The stuff in the modern room is all particle board. Kids' toys, modern room, all plastic. Legacy room, made of actual wood. Did we miss a video in there? Okay, so we're skipping the side-by-side room and we're going right to the side-by-side house because the side-by-side room is too boring. So what we did here is we did the same exact thing except we did it in two 1,200 square foot houses. So two houses side by side. The important things that we're looking for here, we light them both with a small match. We're looking for how long does it take for the fire to run out of oxygen, and then from when we give it air until when it goes to flashover, what is that time period? And that begins to give us our operational time frame that we have to work within to coordinate our attack. So you can see we're 5 minutes in. Your modern fuel, we're blacked out. We've got zero visibility in that entire house. We're beginning to run out of oxygen. Legacy room, you've got white wispy smoke. It's trying to grow. It's getting there. What we did is from the moment that fire began to run out of oxygen, we gave it 3 minutes, and then we went ahead and simulated fire department operations. The simulated operations are opening the front door at 8 minutes, opening the front window at 8 minutes and 15 seconds. Allow that fire to respond to the oxygen and see how long it takes to go to flashover. In this case, about 2 minutes, 15 seconds, we go to flashover. So you see 5 minutes to ventilation limited, another 2 minutes and 15 seconds from ventilation to flashover. So best case scenario, everything's sealed up, fire runs out of air, 3 minutes later you show up. You need to be putting water on that fire in that first 2 minutes to make sure that fire does not go to flashover. Ideally, you want to do it in the first minute so that it never increases in size, it continues to decay. Legacy fuel. All right, now it's getting painful. We're at coming up on 18 minutes and you still have visibility in the fire room. You've got fire that's on one sofa trying to extend to the other sofa. We had some flames roll the ceiling, but it starts to run out of oxygen. Pretty much at the 20, 21 minute mark is when the temperatures start to decrease. It starts to starve for oxygen. So at 24 minutes, we're going to go ahead and open it up. Front door, front window. See, we're finally starting to black out inside. We go ahead, we open it up. You can see the smoke lifts quite a bit. You get pretty good visibility all the way back into the kitchen area. Fire is still confined to one sofa and some carpet. It's going to extend to the second sofa. And we're waiting for enough energy to be released at the same time that the fire is starved for oxygen and has to burn to the openings, has to burn to the front door and burn to the front window in order to get air. Pretty soon you're going to see me and my lab tech have a conversation. Do you think it's going to go? I'm not sure. Do you think it's going to go? I'll go look. And it goes ahead and transitions because it finally got the front 2 chairs going. So what's our timeline? Well, it takes 4 times longer to begin to run out of air. Who's got response times where you can get the call, get to the scene, get a line off, and get it in operation in 20 minutes? I hope there's a lot of hands going up. That's reasonable, right? How many people can get the call, get out the door, and get water on the fire before the 5-minute mark? Not many. And if you got your hands up, it's because you're sitting on the rig, someone tweeted, couch is on fire, and you stumbled across the street and stretched the line. Average response time in the U.S., 6 minutes. That doesn't include the time to get the call, the time to have it witnessed, the time to process the call, and the time to get you on the road. All these things add up. So ultimately, once you vent it, you had 8 minutes and 30 seconds until it went to flashover. How many people, even if your trucks and engines don't even know each other and don't even train together, could probably figure out opening up the house and getting water on the fire in 8.5 minutes? Probably. To say that firefighting used to be somewhat easier, I don't know that I'll go there, but the timeline is shrinking. Your coordination window is shrinking because of the fuel loads that are in today's structures are changing. And now we're going to bombard you with an engineering graph. This is easy. A couple things I want to point out. Notice that the modern line, modern temperatures, which is the blue line, hits 1100 degrees before it begins to run out of air. So that pendulum's kicking up pretty high, and when it begins to run out of air, it drops all the way down to about 400 degrees because it's starving. It drops 700 degrees because it ran out of oxygen, and that happens pretty quickly. Compare that to your legacy, which is your red line. That fire's only hitting 400 degrees before it begins to run out of oxygen, and then it drops down to the 200 range. Now we're starting to talk about, all right, well, what are people being exposed to? What are the occupants being exposed to before you get there? Well, you're looking at ceiling temperatures of 1100 versus 400 before the fire runs out of air. Chances of having more people unconscious? Absolutely. Chances of having people close to the fire dead? Absolutely. But there are survivable places in that house, especially if you look at the oxygen. The oxygen's on the right-hand side of the graph. Now we're looking at the green line. The modern oxygen drops all the way down to 5% as that fire runs out of air. The legacy only drops to about 17 or 18% before that fire can't continue to grow. Now you'll start seeing that the temperature that a fire gets to and the oxygen concentration really dictate how much it can burn. So it's very different today than it used to be. Excuse me. Now we're going to continue along with the void spaces. More void spaces today than there has been in the past because of open web trusses and things along these lines. And attic spaces. You're going to see when the fire actually does transition from a content fire to a structure fire, it's got more fuel available to it in the void spaces, and it's got more air available to it in the void spaces because of the construction practices we use today. If you had a fire that used to start in the void, it would only have oxygen from one joist bay. Now it's got the entire void space to pull from. But the thing that I'm more concerned with is not the fire that starts in the void space, because that's slow to begin with, but the fire that starts in the contents and spreads into the structure itself is going to be taken off quite a bit, especially if you look at how our attics work. You've got a whole bunch of fuel. You've got it in a peak shape. It pulls air in low and sends hot gases out high. If you were to build a campfire, that's exactly how you would build it, and that's how we build our attic spaces. That's why attic fires can be so challenging, is because you got a whole lot of surface area and a whole lot of ability to burn and for it to get air. Sheathing. Let's look at the evolution here. We've gone from solid boards to plywood to OSB to asphalt fiberboard to cardboard to foam. Excuse me, I'm getting over a cold. Very different burning. Here's cedar versus vinyl meant to simulate cedar. The bottom pictures are 2 minutes after the top picture. What you're going to respond to of an exterior fire is going to be very different today than it would be in the past. Wall linings, lath and plaster to drywall. The chance of having a structure fire, when we added gypsum board, we now added seams all over that wall. The chance of that fire going from a compartment fire to a structure fire is going to be much greater today. Structural components. We talked about this a little bit earlier. Dimensional lumber, old growth to new growth, density changes, burning behavior changes, engineered lumber. Then all of a sudden, we're going to make the web smaller. All of this is removing mass. All of it's removing redundancy to buy you more time. It's working against you. Now, in order to make it convenient for construction practices, we're going to cut out the webs and things like that so we can run wires and ducts and everything else. Less wood, less burn time till collapse. That's all it comes down to. It's not the gusset plates. It's not the glue. There's less stuff there to burn to maintain structural integrity. It's going to collapse earlier. And it doesn't matter whether it's old dimensional lumber, new dimensional lumber, or engineered components. Collapse should be in your thought process. Insulation. We're moving from a fiberglass insulation to spray foam insulation. New energy requirements, new products in order to meet those new energy requirements. You're going to start seeing foam sprayed on the underside of decks in the attics to go ahead and make that part of the conditioned space of the house. So it's going to behave differently. Here's a test we ran in Delaware County, Pennsylvania. We had one fiberglass roof against one spray foam roof. We were looking at the impact of vertical ventilation. So we pre-cut a 4-foot by 4-foot hole over top of the fire. The fire started in the attic space and it's contained to the attic space. What I want you to watch is the fire behavior that happens here. Because we cut that hole and we put a piece of 5/8 inch OSB over top of it, so it's got like a 50-pound piece of wood covering it up, we ran some instruments to measure the speed of the gases coming out. So there's kind of a low pressure there around the gaps around the piece of wood. And I want you to watch what happens as this fire is involving the spray foam insulation. Pay no attention to that. There's a police gun range there as well. So the fire itself is not shooting gunfire. See the amount of pressure this fire is creating? And you're going to see the fire triangle right in front of you. That piece of wood that's covering up that vent hole is bouncing a foot off the roof. What happened? Fire ran out of air. As it runs out of air, it can't continue to grow and spread. No water's being put on that. So whether or not you showed up 30 seconds before or 30 seconds after, you're going to see very different size up things. And oh, by the way, your structures aren't going to have a 4x4 hole pre-cut for you that you can pull a wire and open it up. So if we didn't have that as a pressure, essentially a pressure relief valve for that fire, where's that fire going? I don't know. We have to do more to figure it out, but it could be through a piece of weak gypsum board. It could be through HVAC vents. It could be any number of ways that that could find a way to force its way into the structure. It could be after you stick a hook in the ceiling, that it gets some air and go ahead and responds very quickly. We've got more to learn on this stuff, but I wanted to show you that fire behavior. Last component, new technologies. Who's got solar panels on structures in their response area? You know how to safely operate around solar panels? If you told your chief that, sorry chief, we're going to have to wait till the sun goes down till we fight this fire, probably not an option. There's some safe considerations. We did an entire project, and you can go to our website and see the results of it, where we burned full-size systems. We looked at what happens when you put a saw through 600-volt DC line. If you put a halogen bar into the panel, how much your gear can protect you, what types of salvage tarps actually work and don't work to cut the power off. But the truth of the matter is you've got 600 volts potential being generated on that roof. It doesn't take much sunlight to do that. You don't know where the wires run in that house to get to the inverter that's changing that from DC power to AC power and feeding it into the house. So if you go into the garage or you go into the basement and you throw the disconnects and that inverter discharges and reads 0, that means it's reading 0 going into the house on the AC side. That system is still energized from the first disconnect all the way back to the panels. So if you get a fire that involves that wiring and you put a saw or you put a hook into those wires, it could be a bad day. But there's ways to deal with that. One of the important things I want to tell you is don't be scared to put water on the panels to put the fire out if it involves the panels. But two important considerations with that. If you're using a straight stream or a smooth bore, you need to be more than 20 feet away. Or if you do have a combination nozzle, you want to put it on a very slight fog pattern to keep that electricity from being able to travel your stream back to the nozzle. So if that's an option, that's absolutely what you want to do. And a bonus to the fire formula, home lots are getting smaller. So we're building bigger houses, and we're building them on smaller lots. So guess what? All kinds of exposure issues in many cases. Combine that with the fact that we're wrapping our houses in plastic and everything else. And I'd like to say that, well, a lot of these are in sprinkler communities. Well, there's not sprinklers on the outside and there's not sprinklers in the attic. So if you get a fire that starts on the outside because of grilling, starts in the garage for whatever reason, starts in the attic space, it's possible that you're going to see some fires that involve multiple structures upon your arrival, because the amount of energy that's being produced on the outside of these houses is tremendous. And it might not look like a lot moving from 10,100 square feet to 8,800 square feet, but the number of giant lots out there on the acres, it's hard to move that number. And we keep moving that number to a pretty small average lot size of 8,800 square feet. So to sum it all up, houses are getting larger, lots are getting smaller, fuel loads have changed, resulting in fuel-rich conditions. Home designs are more open, meaning there's less compartmentation, they're taking advantage of the structural members. They're more energy efficient, multi-pane windows, we're wrapping them in plastic, alternative energy sources we're putting in the basement and strapping to the roof. Evolutions in building materials are changing your fire environment, and they're changing them faster than even us in research that study this full time can keep up with it. As soon as we think we're studying the latest and greatest sheathing material for a house, a new one's in the production lines coming out, and there's nothing that says that energy efficiency is going to trump fire safety most times. So it's hard to catch up. So it's not easy to make the standards keep up, make the codes keep up, make your knowledge keep up with what you're going to be responding to. So ultimately, you have to ask yourself the question, have staffing, training, and tactics changed to adapt to all these changes? And the answer is probably no. And we're going to try and change that, because we're going to give you a whole boatload of information that allow you to understand the fire environment that you're operating in a lot better right now. I'm going to pass it to Dan. He's going to get into the fire dynamics, and then we'll get into tactics.